Okay, so this is my lab 1 on constant velocity. So what is the purpose of this lab? The purpose of this lab is to demonstrate the principle of Newton's second law using the observation / predicted observation of a moving object, in this case a ping pong ball, at constant velocity. This principle states that net force is equal to the change in momentum over the change in time within an interval. In this scenario, if an object is moving at a constant velocity, the net force would be 0. This experiment allowed us to prove Newton's second law to be true by comparing the similarities of the data from the actually observed movement and the predicted movement. So these are some of the equations that I used. As you can see, I calculated FNet, which I talked about a little bit earlier, as a change in position over the change in time, which I then can use for the velocity update formula and position update formula, where I take the information from tracker, then to input it into the computational model, which I will show in a second so I can demonstrate the data. So in the procedure, I recorded the movement of a ping pong ball, tracked the observation using tracker, collected the formulas, and then used the code in the computational model in GlowScript so that way I could project the expected output, and then created a graph comparing these two data so I could track and compare and reach a conclusion about the accuracy of Newton's second law. So the system and the surroundings. The system is obviously the ping pong ball, and the surroundings are the table and Earth, its gravity and air resistance. So in tracker, I was able to establish an axis, as you can see in pink, and track the ball's position from each frame, as you can see in the bottom right, for each interval of seconds and where exactly the position is. Using this data, I was able to gather the initial time, initial position, constant average velocity that I needed for my computational model. So using GlowScript, I was able to calculate these things, as you can see in the bottom left, observation start time, ball initial position, ball initial velocity, using that formula that I was talking about, and time of last observation. So that way I could use this code in the computational model using the velocity, position, and position update formulas, so that way I can calculate exactly how it expects using Newton's second law within the time for the position of the ball where it would be located. So using this computational model, I can see in a perfect world without any air resistance or any other outside factors what it projects to look like. So the similarities and differences. As you can see, I updated all this data into a spreadsheet and created two graphs. The blue shows the observed position and the purple shows the predicted position. And as you can see, we can tell that Newton's second law is true by its similarities. As you can see in the beginning, it starts off really close, but then it starts to deviate a little bit, and that just shows exactly where it starts to fall below, showing why there can be some errors. So some errors that can come up is human error. So that could be in calculations that I made, rounding with it, or just a tracking error. Sometimes with tracking, with selecting the dots, I could have moved a little bit too much to the right or the left, or sometimes there's the outside factors that we can't consider with gravity and air resistance in a predicted model that actually do happen in the observed model. So some what-if questions that we could ask. What if you flip the axis? So if you flip the axis, the speed would stay the same, but the direction of it flips. So the slope in result would be negative. But the physical magnitude of the speed would stay the same, or of the ball would stay the same. Can you really tell the amount of forces acting on the system? No. Even though the net forces add up to 0, we could have 2 forces that add up to 0, or maybe 10 forces that all add up to 0. We can't confirm how many unless you're actually looking at each of them individually. So in conclusion, we were able to determine that Newton's second law is a highly effective way to model constant motion by showing the similarities between the predicted and the observed model for real-world interactions. And the only differences that we saw was in stuff like friction, but you can see that because the graphs were so similar, we can avidly use Newton's second law as a great demonstration of motion.